Good morning, everybody, and welcome to this weekly EMinar, which is by Karen Weitemeyer on autonomous underwater vehicle-based electric and magnetic field measurements applied to geophysical surveying and subsea structure inspection. Got to apologize to those of you who came in early. We had a little bit of a mishap. We went live before we meant to in our practice session, so I had to stop that. So you had to log in again. So today's speaker, Karen, she's very experienced in EM measurements, now works for a company, Ocean Floor Geophysics, since 2017. Got a honors degree in geophysics from UBC, and then went on to Scripps, UCSD, and got a PhD in 2008. And since then, she's got 10 years of worldwide experience in collection, processing, and modeling of marine EM data. So wonderful to have Karen here. Next week's EMinar will be by Xavi Garcia, and this is an educational one on fundamentals of time series analysis for transfer function estimation. And then in the new year, we have Alan Chave giving a more advanced presentation. And then a week after that, Ken Witherley from industry talking about copper porphyry exploration and magnetotellurics within that. And then the next day we have a very special event, which is something that MTNet will be doing together with the BC Geophysical Society, which is a discussion. We're going to have 4 of the top people in time domain electromagnetics talking about this very specific problem of the on-time step response and low frequency B field late off time. So that would be really interesting. The time's unusual. It's actually, as you can see, it's 30 minutes past midnight UT time. So it's actually in the late afternoon in North America. It's in the morning in Asia and Australasia, and unfortunately it's the middle of the night for Europe. And then the week after that we have Hao Dong giving the last talk before Christmas on 16th on the MT national MT program in China called Sinopro. Just to remind you, I think probably everybody knows now that you can go to the EMinar webpage and you can see the upcoming webinars and also the previous ones that are being recorded, and this one hopefully is, yeah, it's being recorded. Just to remind those of you who are not familiar with webinars, perhaps they're a bit different from Zoom meetings. There's a chat function, so you can send a message, which primarily goes to the panels. There's a raise hand function if you want to speak. And possibly at the end, if you want to voice your questions, you can raise your hand. And then there's a Q&A function. So if you have questions during the talk, you can put them in the Q&A, and Karen might answer those on the fly, or might answer them towards the end. Okay, so I'll stop sharing my screen. Karen, if you'd like to put your video on and your voice on and share your screen and introduce and say hi.
Hello, everybody. Let me just get this organized here. And we'll share and slideshow. Okay, I think I'm sharing my screen with you, and you should be able to see everything. Is that right?
Yep, all good, Karen.
Okay, good. Yeah, so thanks for the invitation to give the talk today at the EMinar. Today I'm going to talk about underwater, autonomous underwater vehicle-based electric and magnetic field measurements as applied to geophysical surveying and subsea structure inspection. And this work is really a collaborative effort with many groups, including Scripps Institution of Oceanography, Fukuda Marine Salvage, ISES, which is a cathodic protection company based out of Malaysia and Aberdeen, as well as DOF Subsea. And so I have to thank my co-authors who also helped put together this presentation, Brian, Peter, Steve, and Matthew. And so the AUV-based electric field measurements actually came about from the marine controlled source EM method, where we have a deep-towed transmitter and an array of electric field receivers. And the three-component electric field receiver, also called a Vulcan, actually is towed some 100 meters or up to 2 kilometers behind the transmitter. And it's mainly been used for looking at marine gas hydrate deposits. And it's a very quiet platform for making these electric field measurements. And so this system was actually used in the Gulf of Mexico, and I'm showing an example of a resistivity section from Peter Camberg, where they used the system to map hydrates at Orca Basin, and he's seen elevated resistivities near the seafloor that could be associated with seafloor gas hydrate deposits. And so Ocean Floor Geophysics has operated the Scripps Vulcan system on several occasions off of Japan, and that's just a photo of us preparing that equipment. And so this really seeded the idea of attempting to make these measurements from an AUV. And I should specify that this is a very OFG-centric talk, and so it's really talking about our development of this method. And so in 2014, the first commercial controlled source EM Vulcan gas hydrate survey took place, and this was a collaboration with Fukada and Scripps. And it was during this time that discussions began about putting the electric field sensor onto Fukada's Deep One AUV. And shortly thereafter, there was a field trial of outfitting their AUV with an electric field sensor. And this was mainly to determine if it was a quiet enough platform to make meaningful electric field measurements. And this led to a follow-on engineering test where it actually collected AUV controlled source EM and AUV self-potential data at a region off of Japan. And I'll show you some results from that particular survey. During this time, Ocean Floor Geophysics also started to look at pipeline mapping because they purchased a Huygens AUV. And so the Huygens AUV is well suited for pipeline mapping. It's also got a little bit tighter restrictions on what kind of instrumentation you can put on it. So we started to look at how we could integrate the electric field sensor a little bit more closely onto this AUV with the purpose of looking at the cathodic protection system on a submarine pipeline. And so we had a field trial, we had noise tests and then a field trial over a North Sea pipeline. And I'll show you the results from that survey too. So all this work led to some commercial surveys from basically our mineral exploration side of things, where we carried out several AUV self-potential surveys last year. And then we also had 2 commercial pipeline surveys. And now, more recently, we're actually looking at applying our electric and magnetic field sensors for characterizing the electromagnetic signature of basically Navy warships. And so the transition of the electric field sensor elements that's used in deep tow CSEM began in about 2015, where we put them onto the Deep One AUV. And in this case, it was mostly a noise test. So here's the Deep One AUV. You can see 2 dipole antenna across it that are creating both a cross line and an inline measurement. And this test was just to determine whether the Deep One AUV was a suitable platform for measuring electric fields. Turned out to be a suitable platform. And so this led to a test in 2016, where now we're adding a vertical pole and we're measuring all 3 components of the electric field. This work, you can see that these poles actually, it's not normal for an AUV operator to allow you to put this kind of equipment onto their AUVs. And so it causes a lot of drag, these poles. And so in 2018, when we carried out some commercial surveys, we added fairings to sort of reduce the drag and allow the AUV to move a little more efficiently through the water. And then finally, we have the tighter integration where now the electrodes are on the skin of the AUV, shown here. And the most recent configuration is shown here with a trial on the Solus Deep 1 AUV, where we're using even smaller electrodes and a little bit tighter fitting to the AUV to make it a little more hydrodynamic. So the main components, first of all, you need to have an autonomous underwater vehicle, and we've fitted this equipment onto more than 10 different types of AUVs. You need to have a self-compensating magnetometer. In this case, we're using a 3-channel flux gate magnetometer with a 19 Hertz sample rate. We have basically the DAC, the data acquisition unit, which takes the 6-channel electric field readings and records them and samples it at about 100 Hertz sampling rate. This also interacts with the AUV's topside computer, and the AUV computer actually record the data as well. We need 6 low impedance silver chloride electrodes, and that's shown here. And then we need to configure it onto the AUV. And in this case, we're configured so that we can collect all 3 components of the AUV. We have a port and a starboard inline component. We have a fore and aft crossline component. And then we have 2 quasi-vertical components shown here. And the placement of the electrodes onto the AUV actually does require some careful consideration. You want to be away from the prop and away from other sensors that are on the AUV that could cause electrical noise on this measurement. And so this is just 2 spectra plots where we have frequency and the power spectra on one axis. In this case, I've converted into a microvolt per centimeter, so a sort of a dipole measurement. In this case, we're looking at shorted noise input. So we're just looking at the digitizer and amplifier behavior. The amplifier itself has a programmable gain between 1 and 128. And our sample rate can be set between 10 and 200 Hertz. And so with a shorted noise input, we have about a 12 nanovolt root mean square per root Hertz at 1 Hertz. That's the type of signal expecting. But when we hook it up with the electric electrodes and actually deploy it on an AUV, we get this this sort of behavior here, where we're now at 500 nanovolts root mean square per root Hertz at 1 Hertz. Now for the AUV self-potential and the AUV integrated cathodic protection, which is just the same thing in electric field measurement, we're interested in frequencies below about 1 Hertz. But for the AUV controlled source EM, we're interested in frequencies above about 1 Hertz. And in this location, you'll see that there are actually several noise peaks from the AUV. And so it's important to actually tune what your transmission frequencies are going to be from your seafloor transmitter. And so we will spend some time in a patch test determining the noise characteristics of the AUV and determining what the best suitable transmission frequency might be for the survey. You can make adjustments, but it sort of requires some tuning. So as I mentioned, we also have the self-compensating magnetometer, the 3-channel flux gate magnetometer. The AUV itself is actually quite a magnetically noisy environment, and so we need to remove the magnetic field that the AUV is producing from itself, basically. So this will involve a calibration maneuver where you basically will do a calibration square. You'll have basically a 100-meter line segment, different headings. And during that 100-meter line segment, as you traverse the square, you'll change the altitude and the pitch of the AUV. So you basically want to get the magnetometer excited by the different movements of the AUV so that you can compensate for the magnetic fields. So you compute the coefficients, you go out and you collect your survey data. This is the raw survey data. You can see basically a striping pattern in it, and you can't see much from the magnetic effects of the seafloor geology. But in real time, you can correct for it, and you get a more meaningful map of what the magnetic fields are due to the seafloor geology. And so more details of this can be found in Steve Bloomer's IEEE report. And so this is just a noise spectra for this fluxgate sensor, and it has about a 0.04 nanotesla root mean square per root Hertz. And the calibration maneuver itself can be applied to other magnetic field sensors that might be put onto the AUV. And so using these two methods, or these elements, the electric and magnetic field sensing elements, we can carry out geophysical surveys. In this particular case, we're looking at mineral deposits and mineral exploration. And the two methods involved are the AUV controlled source EM and the AUV self-potential. In one case, you have an active source that's creating an electromagnetic field. And the second, you're looking at the natural self-potential fields that may develop. And so we've carried out engineering tests in both cases and also some commercial surveys. And in last year alone, we collected over 3,900 line kilometers of SP data for the Norwegian Petroleum Directorate. So I'm going to speak about an example data set from the Iheya area in the Okinawa Trough off of Japan. And this was work first presented by Steve Bloomer and Steve Constable. And so here we have our survey area. We're just off of Okinawa here. And what's really great about the AUV is not, I'm just talking about the electric and magnetic field sensors, but you actually collect a whole suite of other data. We collect multi-beam bathymetry data, which is shown here. We collect side scan sonar, sub-bottom profiler data. You can also collect water chemistry data and turbidity data. And so we're just adding to the payload and sort of adding to the richness of the type of data that you can collect simultaneously. And so in this particular region of Iheya, we have very interesting seafloor bathymetry. We have some of these sort of chimney-like structures or cone structures that are forming along this linear location. Oh, I should mention that this is a back arc basin. And so it's a region with known hydrothermal fluid circulation, and also an area with known seafloor massive sulfide deposits. So I should have prefaced that earlier. Either way, this is why we chose this area as a good engineering test of the system. And so here's just a layout of the survey that was conducted. So we had two seafloor transmitters, also called doozies, deployed underwater electromagnetic source instrument, and they transmitted at 2 and 2.5 Hertz, and they're located here and here. And then there were 6 main AUV survey lines running this way and that way. And the AUV carried out the survey at a 70-meter altitude with 100-meter line spacing. And with the antler electric field sensors on it, it could go at about a 1.1 meter per second survey speed. And we had basically repetition on these lines, so we collected about 20 survey lines, and this was all done in about 7 hours of survey time. And so in AUV controlled source EM, we have a deployed transmitter that will transmit electromagnetic field across its dipoles. You have a AUV fitted with the 3 components of the electric field, and it flies by this deployed transmitter at about a 70-meter altitude. We picked the 70-meter altitude in this case because of the very rough topography and not wanting to get any closer to some of those structures that may stick out about 30 meters from the main background bathymetry. And so this is the photo of the doozy transmitter and a photo of the AUV. And this was, again, done in collaboration with Scripps and Fukada. You can also deploy fixed receivers if you'd like to also make some measurements on the seafloor. And so here we have the schematics of the AUV. We have a vertical pole. It's about 90 centimeters dipole. We have this crossline pole that's almost 2 meters across. And then we have these inline that are about 1.5 meters across. And we get 2 inline components in this particular case. And so this will fly by the deployed transmitter, and the transmitter itself will have excitation on the y-axis for about 30 seconds, and then on the x-axis for about 30 seconds. And these are battery powered, and they can put about 20 amps of current out, and it used a D waveform for the transmission, has about 10-meter dipoles. And we can specify the frequencies between 1 and 10 hertz. In this particular experiment, we use 2 and 2.5 hertz. So basically, the AUV will move past the transmitter. When it's far away, it's down at the noise floor, the system noise floor for it. And then it'll ramp up as it gets closer, and then as you move away, go back down into the noise floor. You can see sort of this jagged kind of pattern in the electric fields, and that's just a result of the changing dipole. So it's changing to the orthogonal dipole excitation, so you get a different electric field measurement. And so this is just the general processing workflow. You have your time series, and you can see the D waveform in here. This is about 3 seconds of data. We have the cross line, the 2 inline, and the vertical. And because we're transmitting at 2 and 2.5 hertz, we have to select a suitable FFT window. In this case, I picked about 2 seconds, and we processed the fundamental and harmonics from that D wave. And we correct for the amplifier response. We normalize by the source dipole moment and ideal square wave. We correct for the receiver drift and the transmitter drift. And then you get basically an amplitude and phase plot versus your AUV survey time. And again, you can see the changing polarities on each of the channels due to the changing dipoles of the transmitters. And at this point, you can stack the data up to 4 seconds, 8, 16, and 30 seconds are possible. Can't go beyond 30 seconds because you're switching to a different dipole excitation from the transmitter. Then you need to merge that with your navigation. And for our integration of this data with a 3D inversion, we actually want to get the X, Y, and Z components for all the electrode positions on the transmitter and on the AUV so that we can properly model it. In 1D, this doesn't really matter so much, and we can just do some simple 1D half-space models using dipole 1D from Carey Key. You can choose to model the E total or P max, and basically this is the results of that. I've modeled 0.01 ohmmeter to 3 ohmmeters, and I'm showing these different half-space models for it. You can see how the behavior of each of the dipoles changes across the line, and how our electric fields fit into these half-space models. And with that, you can come up with apparent resistivity, and it's actually quite conductive, about 0.2 ohm meters in this case. And so this is a good QC check of your data. This is something that we will typically do, but it's also important to look at the individual components as well to make sure that they're behaving how you expect. So looking at the amplitude and phase of both the EX, EY, and EZ components before you move on to feeding it into a 3D inversion. And so in this case, Steve Constable processed the data, and he processed up the fundamental frequencies of 2 and 2.5 hertz and the 3 harmonics from that. For this inversion, just the horizontal amplitudes were used, and the data was inverted by CGI, and we get this 3D conductivity model shown here. And there's our 2 doozy positions and the different flybys of the AUV in the survey area. And we get conductivities in the range, this isosurface here, its conductivities in the range of 8.9 to 10 Siemens per meter. And it's sort of a very interesting result that we get a quite large conductive body in the center of the survey. So to complement this data, we can also look at the AUV self-potential data. So the AUV self-potential data is a natural fields that we're looking for that might be associated with hydrothermal circulation, or it may have to do with mineralization associated with the sulfide ore bodies. We can sort of think of that geo-battery model that's commonly referred to. And so it's the same AUV, it's the same electric field sensor. It's collected at the same time as all the other data sets, including the controlled source EM data. And these are just different photos of the different ways that we've mounted the electric field sensors onto AUVs, where we've gotten much tighter integration in 2019. And so this is an example of the SP data. We've basically filtered the time series and rotated it into the three northeast down components, although I think this one's in an EDU component point of view. And so we have the cross line, the inline, and the vertical shown here. And I'm just showing you repeat passes. So this section here is showing you lines, this line here with 3 passes on it. And this bottom plot here is showing you 3 passes along this line here. And we see really good repeatability. And we also see a signal of interest. We can look at it, all the lines in map view, and we're getting definitely cross lines in general broad agreement. Our range of the signal is about 0.2 to minus 0.2 millivolts per meter. And so we can take this data, and in this case, Steve Constable processed this SP data, and he basically inverted for the self-potential. So we actually have a field gradient measurement, the electric field, and he has it basically set it up on an irregular grid, because that's what it is, and he tried to solve for the self-potential on a regular grid. And so he got results between 0 and minus 20 millivolts. And then he went on to model this with 3 different dipoles, but actually the dipole lengths were so large that it more looked like a point source, where the surface pole here was actually, the pole here was actually very close to the surface, and is estimated at about, I think 40 or 48 amps of current coming from here. Because we collect all 3 components, you can actually plot the vector fields, and you can see the vector fields pointing away from this current source. If we recall, there was all that, those cone-like structures along here that we're seeing basically a high associated with, or sorry, a self-potential low associated with that. And so it's, this is the potential difference that develops on the Earth's crust due to the natural electric currents caused by oxidation and hydraulic streaming potential. And it can be used to map regions of hydrothermal venting, oxidization of massive sulfides, and seafloor geologic structures that just might be disturbing the self-potential current fields. And so it's important that you collect all 3 components so that you can get a good potential estimate. And so here now we have the self-potential data draped on the bathymetry, and very clearly the anomalous zone is lining up with all those cone-like structures. It could be black smokers, and it's sort of consistent with an idea of a hydrothermal circulation mode for what this response is from. We can look at the SP with the conductivity, and you'll notice that actually the conductive body is to the side of our SP anomaly, which may suggest that this is actually due to some mineralization. And so we can also look at the magnetic field data, and Steve Bloomer processed this data. We're looking at total magnetic intensity that's been reduced to the pole. He inverted it using MagM3D from Scientific Computing. And we got a 3D susceptibility model. Isosurface is shown here from about 0.027 to 0.039. I can't actually see the screen. There we go. And yeah, so we have actually quite low susceptibilities in the center region. We can integrate all these data sets together, and remember, they're all collected in a single dive. We have water chemistry data that's showing evidence of venting. We have the seafloor bathymetry and the self-potential that's draped on top of it. We have our 3D conductivity model and our magnetic model. And there's also other data that I haven't even shown you here. But what's really interesting is that we have a conductive high at the same place as a magnetic low, which makes sense for a region of fluid flow where the magnetite has been destroyed. And so this is a really, really interesting result. And it's, all was done in about 7 hours of survey time. And we collected all this data and actually have a meaningful result to show from it. And so this represents our work that's related to seafloor mineral exploration. But our further development began now to look at transitioning this same measurement onto a Huygens AUV that's used for pipeline inspection and subsea structure inspection. And so this work took place in 2018, and we then developed purpose-built AUV hardware. So the instruments that I showed you earlier were actually all built with the purpose for pipeline survey. Prior to that, we had been adapting the CSEM electric field sensors for our measurements. And so we have tight integration of the magnetometer and electric field sensors. We benchmarked it against the towed equipment, and then we've installed it on more than 10 different AUVs to date. And so for our structure surveys in the AUV integrated cathodic protection, we call it AUV ICP. We're looking at the electric fields that are produced from the cathodic protection system along a submarine pipeline. And then more recently, we've done several commercial surveys for this work. And then just recently, we completed a remote operation. So I was at home remotely supporting a group of people on a ship, collecting some data with an ROV over some structures. And so once again, non-contact pipeline inspection. In this case, the AUV is now 5 meters above the pipeline. So we're much closer to the seafloor, not the 70-meter altitude. We're now at a 5-meter altitude. We have the 3-component electric field dipoles connected, and we're measuring all 3 components of the electric field. And we get all this other data. So this Huygens AUV actually has something called a pipeline tracker that tracks the pipeline. And so you get a very good trajectory of the AUV along the pipe. You get all this other imagery. You get high SAS imagery and multi-beam. And you can see different features along the pipe. In this case, looks like a fishing net got caught on this pipe or left there. And yeah, we get photos and all kinds of other things that will help you with mapping the pipeline. And so the reason why we're interested in this is because they're trying to prevent the pipeline from corroding. And so corrosion is a natural process that happens when a metal reacts within its environment. And in this case, rust, which is an iron oxide, will form, which is a redox reaction of iron and oxygen in the presence of water. And then this iron structure basically weakens and disintegrates. So this is sort of like you have the pipe set up as an anode and a cathode, and it just moves along the pipe. When you have salt or seawater, this rusting is accelerated because the electrons can move much more easily. And so this is just a cartoon of what's happening in a pipe where you have this anodic area and cathodic area. You have the transfer of electrons from the anode to the cathode, where you are losing an electron at the anode and you are corroding the steel. And you basically have this electrical path between the two. And because you're in salt water, you have an ionic path that allows the metallic ions to be transported. And so basically this redox reaction takes place and just moves all the way along the pipe until you've basically corroded it away. You can stop this from happening by turning the pipe into the cathode and having an anode outside of it. So a metal that now more readily reacts compared to the steel itself. And so you will connect this sacrificial metal that acts as the anode, and it will corrode more easily, and it will now protect the pipe. An example of a galvanic anode is the zinc sacrificial anode shown here. You can see it's preferentially corroding over the hull of the ship. And the reason for this is because the reduction potential of zinc is more negative than iron, and so it more easily reacts than the iron. So to prevent corrosion in pipes, this is particular to carbon steel pipes and sacrificial anodes. The number one line of defense is actually the coating of the pipe. So they have a very special anti-corrosion coating here, and then it's surrounded by a concrete that's reinforced with rebar or something like that. And with this coating protection, you also introduce something that could be like a bracelet anode to help protect this pipe from corroding. The design of this is very dependent on the environment that the pipeline is located. And so it depends on the temperature, salinity, water depth, if you're in the wave domain or in the deep ocean. It depends on other biologic and chemical factors that can be taking place. And so the design of a cathodic protection system for a pipeline is actually quite complex. But you want to also monitor the health of this system. And what's traditionally done is an ROV is used, and it has both an electric field sensor, the silver chloride half-so, shown here, and it also has a stab tip, and the stab tip's connected with this remote cell so that you can get both a self-potential reading, or potential reading, I should say, potential reading, and a electric field reading. And so you can also visually assess it and take stabs along the pipe at each of the anodes. And so here's a photo of a stab tip being put into a very active anode. And we can see the measurements of the electric field and the potential versus KP, or kilometer post of pipe. And you can see different activities at each of the anodes here. And so we measure the potential here, and you also measure the field gradient. And using these measurements, you can compute the anode current of the different anodes and the current along the pipe. But it's actually quite slow. It's about 0.5 knots is as fast as you can go, and it requires some calibrations. And you also can't get any information when the pipeline is buried, because it requires you to actually touch the anode. And so we propose to collect the electric field data using an AUV. And the benefits to this is you can go a lot faster, about 3 to 4 knots. And it turns out that our electric field sensor is actually quite sensitive, 0.01 microvolts per centimeter. And because of the pipe tracking technology, you actually get very accurate positioning of the AUV relative to the pipe. And you can make these measurements of the electric field even if the pipeline is buried. And in addition to the electric field, you also get your multi-beam, high SAS, magnetometer data, and still photos of the pipe. And so why do we care? Well, we want to check that the CP system is operating properly. You want to detect any corrosion problems and make any adjustments before a major failure. It can be used for future reference of other inspection surveys and may reduce how many inspections you need to do. And you also need to basically adhere to the authorities and make sure, and they want to make sure that your system is operating properly so that there are no major failures. And so for the AUV ICP system, there's several different inputs that go into computing the cathode current. We have basically the 3-component magnetic field measurement, the 3-component electric field measurements. We have the pipe tracking so that we can get up to centimeter scale positioning of the AUV relative to the pipe. And then you want to generally know the position of the AUV itself, so you need a high-PAP USBL system. And then we need to know the seawater conductivity. And using all those inputs, we can compute the cathode current, and so that we can know what the current is along the pipe. And so this is an example. We had a field test in the North Sea on a pipeline in the North Sea, and you can see the multi-beam track of the AUV as it comes down the slope here and coming towards us. This is a transect across the pipe from the multi-beam, and you can see the position of the pipe. And then in the colored plots here is the total electric field, and you can see it increasing as we get closer to different anodes. So we basically have, you can think of it as these point sources along the pipe, and we're measuring those electric fields from those point sources. So one thing that's we found was really important actually is because we're 5 meters above the pipe actually has its own remnant magnetism. And when we move the electric dipole, or the AUV, past these magnetic anomalies, we actually are inducing an electric field. And the magnetic anomalies are about 50 microteslas from the pipe in this example here, which is quite a large signal. And so this is a plot of the cross-line field where we have the electric field, and we see this big change in the electric field as we move along. We can compute the induced EMF by the magnetic field measurements that we have and the velocity measurements of the AUV. So the velocity cross of the magnetic field will produce an electric field, and that's here shown in blue. And you can see that it's actually reproducing almost identically what we measured in the electric fields. And so we can use that to subtract out the induced EMF from magnetic anomalies. So it could, without doing this, you could get a false reading, thinking that it's from an anode, but in fact, it's actually from the magnetic field of the pipe itself. And so in this example, I'm showing you about 500-meter section of pipe where the AUV flew across the pipe in this direction and then came back. This is the position of the AUV in map view. The reds are the different anode locations along the pipe. And here I'm showing the total electric field. Again, we have in light blue pass this way, or sorry, dark blue pass this way, and it passed that way in the other colored blue. And we get very good repeatability, or almost one on top of the other. And then we can look at the 3 different components of the electric field itself. And we can look at this particular location where we have an anode response. We have the vertical fields dipping down, the inline fields changing basically shape across that as it goes across that point source. When you go back, it's an opposite direction, so you have opposite high and low. And we can also look at this characteristic here, which is in the cross-line component, which is actually that magnetic field induced EMF shown here. So just again, this is now the radial field being shown, and in and out of the AUV across the pipeline. And we have very good accuracy, about 0.01 microvolts per centimeter. The standard ROV system has about plus or minus 1 microvolts per centimeter. And so it's really, very sensitive measurements. So I'm sort of showing you the same graphs over and over again. So here now is I've split out the inline component here, and the cross-line component and the vertical component. And you can sort of do the mental exercise of what the electric fields might look like when you move past this anode point source. And so the inline fields will actually dip down as you get close to the anode, and then dip up, or go up and then go back down to the background as you move away. The crossline component, it really depends what side of the anode you're on, what the electric fields will look like. And then for the vertical, we're using a northeast down frame of reference. And so as we approach that anode, we get a low or negative field and then go back to the background. And so you can look at the standard deviation between the different measurements that are made in the opposite direction. And they're all, about 0.02 microvolts per centimeter. And it's really, really cool. So here's just another example where we're looking at different geometries of the AUV relative to the pipe. So in this case, we're 30 meters altitude and 70 meters away, and we're basically in the far field, and the electric fields are all 0. As we get closer to the pipe at a 5-meter altitude and directly above it, those are what most of the data sets I've shown you. Or you can look at the 5-meter, where you're 5 meters across line. When you're in the cross track, you start to get some of the vertical component into that crossline component. And finally, we can get really close, a 3-meter altitude, and you can just see that the signal scales with distance. So at 3-meter altitude, we have the largest signal, 5, and then when you have your cross track further away, the electric fields go lower. So everything's making sense. So we can also, as I said, compute the anode current and can use a simple Ohm's law relationship to do that. And in this particular case, we're getting just under 0.01 amps coming out of this anode. You can use that to predict the anode end of life and basically compute the mass and energy remaining within the anode. And so now I'm just going to show different sketches of AUV ICP operations that we saw in a survey in 2019. Can't show you the real data because it's confidential, but they're nice little examples of what we might expect to see when you have a missing anode, or you might have current drain to a structure, a short pipe response, a missing anode, or a well-protected long pipe. And so in this case, we have a missing anode. The red are the different anode locations. We're likely approaching a structure here, so you get really high electric fields because there's a lot of anodes on that structure, and there's a lot of current flowing to try and prevent that structure from corroding. And so because you're sort of expecting a regular pattern of the anodes, you can notice when there's one missing. And so in this example, there actually was a disconnected anode, and they can find that out by looking at the photos that were also collected during the AUV survey. In this case, we have a drain to a structure, so you basically get an elevation of the electric fields, which results in an increase in the output current from each of the anodes. In this case, you might have different spacing of anodes along the pipe. So this might, say, be a 25-meter anode spacing, and this might be a 12.5 anode spacing. And because it's just, the summation of all these different point sources, in this case, you're just getting very elevated electric fields and subsequently elevated currents. And so within this section, again, you're missing that pattern of having all those anodes showing up. And in this case, there's one missing. And then this is a typical short pipe, so you might have structures on either end. And so you basically get an elevation of your electric fields on either end associated with those structures, and increasing current. In the case of a well-protected long pipe, the structures might be over here on this end. And basically there's very low anode output current and very low electric field strength. And so it's quite boring, actually. And so with this in mind, you can carry out sort of 3 different scenarios for where this might be useful. One might be in a maintenance survey where you're trying to determine the current output from each of the anodes and to determine its remaining mass and anode life, and whether or not you might need to start thinking about replacing them. You can use it for an intervention survey, so you can do a rapid assessment of the current condition of the pipe. Say something might have happened, and you can take the AUV out and go survey quite quickly. Or you might use it for baseline surveying or tying in with other measurements. And so it's important to think about this. The ROV traveling up at 0.5 knots, whereas we're traveling here at 4 knots, it actually saves a considerable amount of time and money to survey a pipe in this fashion. And we're probably talking like a significant sum of money that can be saved for looking at the cathodic protection system with an AUV instead of with an ROV. And so basically, our work is split into mineral exploration and subsea structure inspection. And as I mentioned, now we're currently looking at using the same electric and magnetic field sensors to basically have a mobile range that will allow us to measure the signature of different warships so that they can basically, instead of going to a mobile range, they might be able to use a deployed system that will allow them to correct for their magnetic and electric fields so they can basically hide themselves. So I think I've shown you that an AUV is a very efficient collection system that allows you to get multiple data sets simultaneously. We've got basically two main techniques. AUV-SP and AUV ICP is suitable for both focused and regional scale studies. The AUV-CSEM is really more suited for very focused studies over a small area. Other applications that allow us to characterize the ship signature I mentioned, and then we've just recently put the same sensors onto an ROV. And so that concludes the presentation. I saw a lot of things come up in here, and I'm sorry I didn't stop, but I can take your questions now. So I guess I do go here.
Well, thanks very much, Karen. That was absolutely wonderful.
Good.
I hadn't realized that you go so far on the subsurface. We've got a couple of questions in. You can probably see those.
Yeah, I've got one here.
One from Chris Nind of Abitibi Geophysics. What are you using for positioning and how good is it?
Yeah, so it sort of depends on what we're doing. For the pipeline survey, we definitely need to have the HiPAP system installed on the ship, and you can probably get good positioning to 1 to 2 meters for the AUV. And for the mineral exploration, it depends what ship you're using, how good its navigation system is. But I would say in our example, it might have been a 5 meter accuracy. Yeah, so hope that answers the question from Chris.
Pascal makes a comment about usually pipes have
that's
isolating
correct.
coating. Yeah, and you kind of covered that.
Yeah, that's correct, Pascal. They do, and that's the main line of defense for the pipe. But that can be damaged, and so that's why you also have the anodes. Okay. I have one. Should I say it or should you say it? I don't know.
It's you and everyone should be able to see them.
Yeah.
If everybody looks at the Q&A, you can see these questions popping up. But there's one from Sergio. Could you please explain again how you calculate the vectors in the SP measurements?
Yeah, well, basically we measure, the AUV has a very good navigation system. So we have the heading, the pitch, and the roll of the AUV. And so we also know the position, the positions of the electrodes on the AUV. And so we can basically rotate our electric field measurements into an NED frame of reference. Is that good? Yep.
And Raha asks about the how do you take the problem of induction of magnetic field in pipelines?
Yeah, well, I think I showed you an example of that, and we remove it. So we measure, because we're measuring the magnetic field, and because we get the velocity of the AUV, we can compute the induced EMF and remove it from the electric field measurements. It's all good questions.
I've got a question. If
Yeah.
at your source, you excite in one direction for 30 seconds and then a perpendicular direction for 30 seconds. I just wonder why you don't excite both directions simultaneously, but perhaps use a different shape
Frequency
for the waveform.
Yeah. That's possible to do, I would say, but I think the complication at the time of implementing that, we decided not to do that. So we tried to keep it simple for this first engineering test. But it is possible to do that. One of the problems is working around the noise environment of the AUV. And so we could be limited into what frequencies that we can transmit. And so that could be, a balancing act that has to play out.
Yeah, just again on the waveform, you use a square waveform.
Yeah, we're using the D wave in this case. Yeah.
I just many years ago in the mid-70s, Gordon West had the idea that in fact you want to measure dB/dt, so why not use a triangular waveform? And that's the basis of the U10 University of Toronto EM system, where they use a triangular waveform shape. Because you can much more control a ramp than you can a step on, step off.
Oh, in terms of creating the waveform.
Yes.
Yeah.
Okay, is there any other questions from the audience? We'll see, we have we had 40-odd people, 48 people in, so, and there's still 43 of you there.
Great.
Any other questions from any other participants? No? Okay, well, thanks very much. Oh, wait, somebody just popped up.
One came in, let's see.
Yeah.
Oh, there we go. What
about water pollution and resistivity change effects? Oh, that's a good one.
Oh, well, that is a good one. So we do measure the seawater conductivity, and it is an important measurement for modeling the electric fields properly, both for the inversion point of view in mineral exploration and in computing the currents from the anodes. So I think that's probably how I can address that question.
Okay, thanks very much again, Karen. Oh, so here we go. How compatible is the CSEM with reflection seismics?
So I didn't look at, there's sub-bottom profiler data. I haven't looked at it. I think Steve Bloomer did, and he mentioned the presence of ash layers. But it's not really reflection seismic. So I don't actually have an example with reflection seismic and our AUV-CSEM in this case. But they should be complementary. They'll tell you different things, right? Reflection seismic is going to tell you about basically structures that you can pull out, and then the EM is going to tell you about what's filling the pore space, generally speaking, or if you have a big conductive mineral deposit. Is that it?
Okay, thanks very much.
Yeah.
Karen, I'll just take your
stop share. There we go.
Yeah, I'll just take your screen back and remind everybody that we've got our webinar next week is from Xavi Garcia. It's at a little earlier, a couple of hours earlier from now, so at 1400 UT. And Xavi's webinar will be an educational one on fundamentals of time series analysis for transfer function estimation. So I'd like to thank Karen very much for being with us today and giving us an excellent talk. And I'd like to thank the audience for listening in, and some absolutely excellent questions, actually.
Yep.
So bye for now. Thanks, Karen. Bye,
Yep,
everybody.
thank you. Bye.